What's going on everyone? This is Jay Patel and in this video we will be implementing neural network from scratch in Python. We will be making an application to recognize the handwritten digits so our model will be able to recognize the numbers that these images contain. For example, this is 6 and this is 1. Also, there's a great bonus for you at the end of the video. I will be providing you with an assignment and I've already uploaded it and you can get this from the link in the description. In that assignment, I have provided the blanks for you to implement the complete model for yourself. And I've also provided you with the explanation. For example, here I'm providing you with the details about what does the np.random.randn does and what does the np.zeros does and additional details in the links as well. So there are great descriptions about what you need to do and you can then implement it yourself. You just have to fill out these code lines and at the end you will be able to also check the accuracy of the model by running these cells. And no worries, we will be implementing that entire thing from scratch right now in this video, but at the end of the video you can just visit that link and just click on this download zip file. It will download the entire zip file with the data set and with the assignment, so you just have to complete that code and it will be a great practice for you. And I'm very excited for this video, and if you haven't yet subscribed to this channel, then what are you waiting for? Hit the red subscribe button, also hit the bell icon so that you get notified every Sunday when I upload a new video. And for this video, let's get started. We will start by importing numpy and matplotlib as usual. Then we will load our training and the testing dataset. Let me show you how the dataset looks like. So this is our dataset and this entire row represents one image. It stores the value or the black or white pixel value. For example, all these zeros represents the black region here, and where you see the number which is 254 is for the white region. 254 is for white and a number closer to it is for slightly grayish color. And our training dataset have 1000 images, 100 images for ones, 100 images for twos, threes, etc., so on from 0 to 9. So let's just import it. So to import it, we will use np.load.txt and just provide the file name here, which was train x csv for me, and it will be also same for you if you download the file. And here we are providing with the delimiter, means how we want to separate our data. So our data values are separated from the comma, so delimiter is comma. Similarly, I will import the labels for this training data and the test data set as well. So we have our data set. Let us print the shapes of these. So here are the shapes. This 10,000 represents the amount of data we have or the observation we have. This 784 comes from our image whose size is 28 pixel multiplied by 28 pixel. So which is 784, which will be our total number of input features. And this 350 is the amount of observation in our test dataset. But if you remember, we needed the input shape of the form n comma m, not m comma n. So we will do the transpose of these, and now we have our features properly in shaped. Now our labels y train is 10 comma 10,000. So this 10 represents the one hot encoding, means there will be a 1 at one position. For example, for 0 it will be at the 0th position, for 2 it will be at the second position, and so on. So now we have our data set. Now let us display the image from our data. So to do that, I have made the use of the random library from Python. The rand range will provide us with the one random number between 0 to here, and this xtrain.shape is nothing but a tuple, which is this, and we are extracting the second element from the tuple, which will be 1000. So it will provide any number from the range 0 to 1000, but to use that we will actually need to import random. So let us import random as well, and then I will use imshow function from matplotlib, which is used to display the image. So we need to extract the image of at any random index value which we got from here, and as it is a array with a 784 element, we need to reshape it to 28 28. And then plt.show, let's try and run this. So it displays our image well, but the color map is not that well. So to get the image in the gray map, we will use color map and set it to gray. Now every time it will display a random image to us. For example, when I run it again, it displays 0, and if I run it again, it displays 9. Now we have our data and we are all set to implement our model. So here is a summary of our entire model. We will be using a neural network with only one hidden layer in this video. In the next video, we will be taking a neural network with multiple hidden layers. For example, we will be making an application in which we can change the number of hidden layers, and we will also test what will be the effect by changing the number of hidden layers in our model. But in this video, we will be only taking one hidden layer. So these are the equations for our neural network, and I have provided a great in-depth explanation about how these equations came, along with all the mathematics behind it and the intuition behind it as well. So make sure to check that out if you haven't already. I will provide its link. I will provide the link for that playlist down in the description. In this video, I will just quickly summarize what we will be doing. So we will initialize the parameters randomly, W with the random values and B with the zeros. Then we will be repeating all these below steps for multiple times, and these below step includes the forward propagation, and these are the equations for the forward propagation. We already came up with these equations in the previous videos. This is the softmax function, and we will be using this loss function, and the cost function will be given by this equation. So this is the softmax and this is the softmax cross entropy function or categorical cross entropy function. These will be the equations for the backpropagation. We already derived these equations. In that we have two hidden layer model, and in this we only have one hidden layer model, so we will be starting with dz2 instead of dz3, and then finally updating the parameters. So we will be making a function for all of these things. So let's start making them. For first, I will be making the functions for activation. For example, for tanh activation function, and for tanh we will be just returning np.tanh. Then value activation function, which can be given by np.maximum of x or 0. We can implement either of these two functions in our hidden layers. Then we will be making a softmax activation function by taking the x, then exponential of x, and then returning by np.sum exp x. Now we also need to find the derivative of these tanh and ReLU activation function, because here this will be the here it should be f dash of 1. So f dash of 1 is the derivative, so let's make the function for that as well. And if you remember, the derivative is nothing but 1 minus of a square, so that's what I will be returning. So if the input is x, then just return the x square. And for ReLU, if we have, let's say, this array, and if we just do a greater than 0, then it will return an array with the true and false, where it shows if the a is greater than 0 or not. We can just change these true or false into zeros and 1 value by taking an np.array and mentioning the data type, which will be np.float32. So if we do the same here, it will make the 0 for all the values less than 0. Now we will make a function to initialize the parameters, and we will be giving the input nx, nh, and ny. So this nx is the number of neurons in the input layer. This is for the number of neurons in the hidden layer and number of neurons in the output layer. So we want to initialize the w parameter with random values, and this can be done by np.random.randn, and this returns an array or the matrix of the dimension nx, nh. But its value can be very large, so I will be multiplying it with 0.01 to make the values small. You can see when we run this, it gives the matrix of size 4, 2 with the random values. Then b1 will be nothing but zeros of shape nh, 1. And similarly, we will be getting w2 and b2. Now we need to return these parameters, but there are a lot of things to return. So instead of returning like w1 b1 individually, we will take a parameter dictionary in Python to store all these parameters in this dictionary. So w1 will be given w1 and so forth, and then finally just returning this parameters dictionary. So we have this. Now let us move on to forward propagation. So for forward propagation, we will need input x and the parameters here that we got, and we need to just implement these equations, and we also need to extract our parameters from this parameters dictionary. So to do that, I will just write parameters and the name of our parameter, which will grab us this w1. Similarly for others, and then implementing the equation z1 will be given by the matrix multiplication of w1 and x. So to get the matrix multiplication, we use np dot provides the matrix of these two, so it will be a matrix multiplication of w1 and x, then doing the sum with b1, then passing this z1 into ReLU activation function, which we already made above, and then similarly z2 will be the matrix multiplication of w2 and a1, and then b2 here, and then a2 will be passed to Softmax activation function. So now we need to return these z's and a's. So for that, we will also take another dictionary. I will name it as forward cache. So I have stored our variables. We will just return the forward cache. So our forward propagation is done. Now it's time to implement the cost function. And the equation for the cost function was this. Let's quickly implement it. It takes the input a2 and y, which are our actual labels. Then we require m, which should be the total number of observations. So for that, we'll just take y dot shape, which will shape and grab the second value in it. So that will return 1000 for training. Then cost will be equal to minus of 1 by of m multiplied by np.sum of this, and then again the sum of this. So this is the row wise summation and this is the column wise summation. So we can just pass it into np.sum and it will give the sum of the entire matrix, which is what we want. Here y multiplied by np.log of a2. You can take two sums, and this 0 is for the row wise sum, so it will be this, and this 1 is for the column wise sum. You can take this or this, both represents the same thing. So cost is also done. Now it's time for backpropagation, and these are the equation for this. This is for the output layer and this is for the first hidden layer. So for the input, we need x, we need y, we need all these a's and z's, and also the parameters w's and b's. So we will get everything, and then I will extract our parameters and the forward cache. And we also need this variable m, which should be the total number of observations. Now it's time to implement tz2, which is nothing but a2 minus y, and the w2, which is 1 by m multiplied by matrix multiplication of tz2 and a1 transpose. Then db2 will be equal to 1 by m, then the summation, which is a column wise summation, so dz2 and x is equal to 1 means column wise summation, and we'll also make it keep dims equal to true. So this keep dims forces the np.sum to return a proper shape. For example, I've taken an array here a, which is just any values, and if I print the shape, then it returns the 2 comma nothing shape. So we need to make the keep dims equal to true so that it returns a 2 comma 1 shape or the n2 comma 1 shape for here. Then dz1 will be, sorry, this should be 2 not 3. So dz1 is 1 by m multiplied by matrix multiplication of w2 transpose and dz2, then element wise multiplication of derivative of our activation function, which we used relu, and a1 here, because this f1 z1 is a1 and we are doing its derivative, so derivative of a1. Similarly, dw2 will be nothing but 1 by m multiplied by np dot dz1 and x transpose, and in db2 we will pass dz1, rest the same. Now we will return these dws and dbs by taking a dictionary and then returning this dictionary. Also note, this should be small x dot transpose, not capital X dot transpose. Now update parameters. We will pass parameters and these gradients, these dbs and dws. We will fetch the parameters and gradients. Then update w1 is w1 minus of learning rate, but we didn't pass learning rate here, so we will pass the learning rate and then just dw1. Similarly, I have updated other parameters as well. Now we will update our parameter dictionary with the updated parameters and return parameters, and we are done. Now it's time to implement and combine everything. So we will start by taking our input x, y, then number of hidden layers, which is nh, learning rate, then we will need iterations as the number of times our for loop should run, and that's all. Now we will also get this nx and ny from x dot shape 0 and ny as y dot shape 0. Then we will initialize our parameters by, we had this function here. Then we will run a for loop for iteration times and implement the rest of the functions that we had, first starting with the forward propagation. And we know that the forward propagation returns a forward cache, and the function that we made was then the cost function, which takes the input a2 and y, and we don't have a2, but we can get a2 from this forward cache. So forward cache is a dictionary, and if we just grab a2, we will have the a2 here and y. Then backpropagation, which can be done by this function, and it returns the gradients. And then update parameters, and update parameters returns the updated parameters. So we had forward prop, cost function, backprop, update parameters, which are these functions that we made: forward prop, cost, backprop, and the update parameters. So that's it, is our model. Now after this for loop ends, we will have our parameters trained, so we can just return those parameters. But I also want to return something else, which I want to return a cost list which will have all the cost for every iteration. So for that I will need to define an empty cost list here as an empty array. Then we will append the cost for every iteration in this list, and this will help us to see how our model was learning and if our cost was decreasing or not. And I also want to print our cost, let's say 10 times while we implement this model. So this can be done by doing this I percentage iteration time tens. If you want to print it only for 5 times, then make it 5 here, and also equal to 0. So this will be true for 10 times, and in that cost after iteration is cost. Whew, we have our model. Now it's time to run this. I will take let's say 100 iterations for now. Then nh will be let's say I want it 1000 for now, because our input layer has 784 features. Then I want to have a 10,000 number of neurons in the hidden layer, then 10 in the output layer. Our model returns the parameters. So here I will take capital P for this parameter and capital cost list for this parameter. Call our model by passing xtrain, ytrain, which was our data set. then nh equal to nh, learning rate equal to learning rate, but we didn't had learning rate here, so let's get that as well. Let's say I'm taking 0.005 as our learning rate for now, and then iterations equal to iterations. It says derivative value is not defined because I didn't took v here. Keep dims, I made a spell error. tw1 is not defined. Let's see, because I didn't took tw1, I just took db2 and dw2. Operand could not broadcast. Let's see. Okay, so this should be dz1, not dz2. So I made the error there. Now if we run, there is also an error. So this error is here. Here we are taking np.sum of exponential of x, which is our input, and we are giving z2 as our input. So z2 is of the shape n2 comma m. If we do just np.sum, then it will sum the entire array, all the values in that array. So we need to do actually the row wise sum. So we will have to take 0 as our axis there, and our problem should be solved. And then if we run this again, yeah, so we are getting NaN, so our learning rate is very high. So let us decrease our learning rate. I am making it 0.002. Let us see. And as you can see, the cost increased a bit, but it's okay. Then it steadily decreased, and it is very clear that now it is on its local minima. So let us plot the graph of cost versus iteration. So the cost increased a lot. It might have happened because of some reason. We do not need to worry about it. But then it steadily decreased, and it is almost at its local minima because it is not decreasing anymore. Now let us check the accuracy of our model. So for accuracy of our model, we will need to make the predictions by computing the forward prop. But if you print this A out, then you will see that these are in the form of probabilities. So we need to extract the highest probability, or the index where the highest probability lies. So that can be done by using np.argmax. So argmax return the index in one row having the maximum value in that row. So A out, and 0 specifies that we want to search in the row, not in the column. We can see that we are making predictions, which is pretty good. Now let us check how many times this A out is equal to our Y train. But Y train is also in the form of one hot encoded. So I will have to take this Y out as np.argmax. Now we have all the trues, but it's not nice. So we will take the mean to see how much percentage of accuracy we have. 99.9%, which is pretty good. But we also want to check our test accuracy, so I will make all these as a function. So these are this is our train accuracy, and this is our test accuracy. We can round this off, and we are pretty good to go. Now we implemented this with the ReLU in the hidden layers, so we will now implement it with the tanh in the hidden layers. So we will change this to derivative tanh, this forward prop to tanh. Now running entire thing, training our model again. So the accuracy didn't go down a lot, so we will increase the iterations, or sorry, increase the learning rate. Now maybe it's pretty down, let us check. So the graph is pretty smooth down there, and here the accuracy was 83 and 99. Let's check what is with the tanh. So it is 96, 89, but I think this will the accuracy can be increased even more by increasing the number of iterations. So you can do that, and once you do that, So now you can see the cost is pretty down. Plot the graph, which is pretty good. Check the accuracy, which is very good, 187%, which is even better than that of Reldo. Now we can do another cool thing here. What we can do is we can display an image and make the prediction for that single image. So we displayed our image here. So let us grab that. And we know that we make the prediction with the help of this. Our model says it is 2, good. And our model says it is 8, so it's pretty good. So that's it for this video. Make sure to download that assignment and complete it by yourself. And once you complete the assignment, let me know the accuracy that you got. Most of the people who watch a video tutorial on YouTube do not implement it themselves, but if you are the one who do implement, then comment down below that yes I have, and also let me know the accuracy that you got, and because of your comment other people will also get the moral support to implement it by themselves. So make sure to implement, comment in the below that you have implemented, and let me know the accuracy. And in the next video we will be looking at a model with the multiple layer, and I see you there.